carry out software security. Like, if you're going to do static analysis with a static analysis tool looking for bugs, what do you need to know? What bugs look like, so you can put that into the tool. That's a piece of intelligence. And there are attack models and security features in design we put in there, and then standards and requirements like secure coding standards and so on. Then there are best practices of the sort that are described in software security or Microsoft's SDL book or OWASP, and those go in the SSDL pile. In fact, we called that SDL touchpoints to mergeify kind of Microsoft's approach and my approach. And Microsoft, when they saw that, they said, oh, you can't use SDL. That's sort of a Microsoft thing. That means our secure development lifecycle. And I was like, what? You know, you think you've already made a term like Band-Aid or Xerox? I don't think so, Steve. But Steve said, well, we really would prefer it if you called it something else. So I call it SSDL, which stands for Software Security Development Lifecycle, or Steve's Security Development Lifecycle. You know, your choice on that one. But some of those pretty common best practices, architecture analysis, which turns out to be very difficult and something that's hard, code review with a static analysis tool, or manual analysis, and security testing as carried out by developers and QA people, not as carried out by penetration testing people, which is something that shows up over here post-deployment or at the point of deployment. So we want to cover software security all the way from the executive level all the way to a piece of software or an application that's actually deployed out in the field, and what you do during deployment to make sure that it is secure. So it's a pretty wide grid that we've drawn for ourselves, and the conversations that we had ranged around this archaeology grid, and we found out stuff, right? So we would note down what people said in a certain quadrant, and then we would synthesize those, and we synthesize those into a set of activities, 110 activities, which we observed. Which we observed. Let me say that again. Which we observed. This is a key thing to understand. When you go out in the jungle, you look in the trees, and you see some monkeys. The monkeys are eating bananas. What you observe is monkeys eat bananas. What you do not observe is bananas are good. You should only eat yellow bananas. Don't steal bananas from your friend. Don't run while you're eating bananas. None of that. No value judgments. Not, it's good if monkeys eat bananas. You know what? All we're saying is monkeys eat bananas. So in this model, when we say we observe this practice, we're not saying you should do this practice, or you better do this practice, or even this practice works. What we're saying is we observe this practice. Monkeys eat bananas. Everybody got that? This is completely different than how computer scientists usually tick. Usually computer scientists are trying to project their shoulda, woulda, couldas onto something, or you have a theory and then you build a model to support your theory, which is how most people's PhD theses work. You know, and the software engineering literature is a disaster because of this, because software is so bad that no matter what you do, it's going to find problems in software. So you can always publish, because software is so bad that your stupid idea will work. And it'll get published. And so you look at the software engineering literature, and that's what it looks like to me. I don't know. It's kind of sad. So let's turn that around. Let's just talk about what we see. Let's get away from value judgments and shouldas and faith-based software security and build it on observation. So just to kind of push this point further, we're trying to move to science, right? And what we're starting with is religion-ish. So anybody heard of cargo cults in here? SPAF, of course. I always have to explain this one. Only a few people know what this is. So during World War II, there were these islands, and these islands had indigenous populations on them. And when the Japanese were running around the Pacific, they would invade these islands and build a landing strip and fly their planes down, and so would the U.S. War would kind of go through the Pacific. And when the airplanes came to the island, the indigenous populations were like, dude, we like spam. We like those airplane things. They bring us fuel. They bring us shiny beads. Airplanes are cool. Well, the war moved on, right? The airplanes stopped coming. But these people, they liked the airplanes. So they developed cults around airplanes, and they built like fake landing strips. And this is actually an airplane that they built out of palm fronds right there. And then they would, like, you know, do some ceremonies and hope to call the airplanes back to bring some more cool stuff. That's a cargo cult. Software security today is kind of like a bunch of cargo cults. There's people that fly around that are really good, like SPAF, and they give a talk and everybody gets excited, and then SPAF flies off and the cargo cult forms. And they start like making stuff out of palm fronds. And please, press the little button.
Oh, yeah, so just as a note,
yeah.
On my webpage for documents for grad students, I have a copy of Richard Feynman's address on cargo cults and science.
Beautiful.
So if any of you are interested,
definitely
this is exactly the topic.
It's a very, very important thing to understand, because what we want to do is move away from that and move towards, you know, maybe we've gotten our way all the way to divining rods, right? So, but we don't really know how those work, or really if they work. They sort of seem to, but nobody's sure why, right? But compasses we understand. That's, you know, we understand those. And most importantly of all, there's this thing called a measuring stick, or a thermometer. Let's talk about science. So where did thermometers come from? Well, there was this guy, Kelvin. He got a tube of mercury. It was just a tube of mercury. And he drew some lines on the tube of mercury, right? And then he started making some observations about how tall the mercury was when it was a certain number of lines. And after a while, at least two systems developed that people started using regularly. The Fahrenheit measurement system and the Celsius measurement system. And they're completely arbitrary, just like meters or yards. It's just a stick with some lines on it. So a thermometer is a tube of mercury with some lines on it. But if we all use it the same way every time, that's how we can begin to build hypotheses and then disprove them or prove them later. And that's what science is about. So what we wanted to do for software security, and this is a rather, you know, big undertaking, is to just build a yardstick and have people use the same yardstick to describe what it is that they're doing. So you can think of the BSIMM resulting model as a yardstick for software security. And it seems to be being used that way now, but that's our big plan in the sky to move away from cargo cult security. I got to get a copy of that paper. I always read Feynman's paper about the space shuttle, which is also a good one. But I didn't know the cargo cults one, so I got to get that. Okay. We found some stuff out as a side effect of this work, which was pretty cool. Like, we did ask them, how long you been doing this, how many people you got, and how are they organized, and how many developers are there. And when you do this, you can actually make some observations that provide hard data, which are really interesting. For example, every single one of these initiatives has a centralized software security group. Now, does that mean that you can't do a software security initiative without a software security group? No. What that means is the ones that we observed all have one. They seem to think it works. All right? Everybody clear on that? So, you know, some people come to us and say, should we have one? Well, you want to be like those guys? They have one. And that's all you can say, really. Right? So the smallest one that we observed was a group of 12 guys. The largest one was a group of 100 people. And you can see the median there. Now, the really interesting thing happens when you take the SSG size and you put it over the developer size, and you do a ratio. So we're talking about large groups of developers. The smallest one was 450 developers, and the largest was 30,000 developers. The interesting thing is, when you do the math with all of the real data, you can make a statement. which is that what we observed is that the SSG size seems to be around 1% of the developer size.